Welcome to my talk, Computing Shortest Paths and Diameter in the Hybrid Network Model. I'm Philipp Schneider and this is joint work with Fabian Kuhn. Since this is a fairly new model, I want to start in the first part by giving some introduction and then carefully explaining the model. Hybrid communication networks are very common these days. Consider, for example, a set of smartphones, and these can typically communicate among each other via the cellular network. But they can also communicate directly via Wi-Fi or Bluetooth. In another example, we have a company network, which consists of workstations and servers. And these can communicate directly via the wide area network, but also via the internet in a point-to-point fashion. So we observe that in practice, we typically have two communication modes. One local communication mode, which has a short range, but is fast. And we call this the local network and model it with a graph. On the other hand, we have the global communication mode, which allows for point-to-point communication, but is slow. We call this the global network and model it with a CLIQUE. The hybrid network model is from the family of synchronous message passing models. That is, we have n nodes with synchronized clocks, and time is slotted into synchronous rounds. In each round, each node can do arbitrary computation, but the communication between nodes is restricted. And our measure for complexity equals the number of rounds that we take to solve a problem. So at the core of the hybrid model is its mechanism for message passing. And this was introduced by Augustine et al. Earlier this year. And in its most general conception, the hybrid network model allows for lambda bits per edge and per round in the local network. And in the global network, each node is allowed to send or receive gamma bits per round. And the difference really lies in the restriction per node and per edge. So this leaves us with a large space of different possible hybrid network models. And in fact, in its marginal cases, the general hybrid network model captures various well-known synchronous message passing models. So for example, if we don't allow global communication, but leave the local communication unbounded, we get the well-known local model. If we allow no global communication and polylog n local communication, we get the well-known congest model. If we allow roughly n log n global communication, but do not allow local communication, we get what is called this congested clique model. And the equivalency can be seen from Lenson routing. If we allow polylog global communication and no local communication, we get what is called the node capacitated clique model, which was introduced last year. So this leaves us with a large space of possible hybrid networks. And Augustine et al. Argue that practice is best reflected if we are most generous with the local communication mode, but very restrictive with the global communication mode. So they define the hybrid model as the combination of the node capacitated clique model and the local model. So in the following, we will have unrestricted bandwidth over the edges in the local network, but only polylog n sized messages over the global network. So next I want to talk about the problem that we're actually solving. So in the distributed shortest path problem, we consider our local communication network as our input graph. And each node is supposed to compute part of the solution, and what this solution looks like, for instance, in the so-called k-sources shortest path problem, is that we're given k distinct source nodes, and each node must learn its distance to every source. For k equals n, we have the so-called all pair shortest paths problem. And for k equals 1, we have the single source shortest paths problem. In the diameter problem, each node must learn the unweighted diameter of the local communication network. And it's important to mention that these problems cannot be solved locally, as all of these problems have the obvious lower bound of omega of diameter. And the question that Augustine et al. Was asking was whether limited global communication helps to solve these problems significantly faster. And their answer was yes. And this leads us to our second part, namely our contributions, where I will show you how we improve on their results. I will start with our results on lower bounds. It's important to mention that even though the hybrid model allows for significant speedups, it has fundamental limits. So we start with a comparison for the k-source shortest path problem. If we are only allowed to use the local network, then the obvious lower bound is omega of d, which is also the upper bound. If we are only allowed to use the global network, then the lower bound is omega of k, which can be seen from the fact that each node needs to receive k distance labels. So in the hybrid network, we observe by slightly adapting the corresponding lower bound by Augustine et al. That the k-source shortest path problem has a lower bound of omega of square root of k, even for very crude approximations. For the diameter problem, in the local network alone, we have the same situation, that we have a lower bound of omega of d, which is also the upper bound. In the global network, we have a lower bound of omega of n, which can be seen by a straightforward adaptation of the congest lower bound. In the hybrid network, we show that we can adapt the worst case graph, which is used in the congest model, to produce a bottleneck in the hybrid network model. And this leads us to a lower bound of n to the 1/3 to compute the diameter exactly, and the same lower bound to compute a 2 minus epsilon approximation of the weighted diameter. So next I want to talk about our algorithmic results. First of all, we showed that we can solve the APSP problem in square root of n rounds, which improves on the roughly n to the 2/3 round algorithm by Augustine et al. Our result is tied up to polylog n factors, which we have seen from the previous lower bound. And we also have seen that reasonable approximations cannot be computed any faster. So in a sense, our paper settles the all pair shortest paths problem up to polylog factors. Our second result is that we show that constant approximations for the k-source shortest path problem are possible in square root of k rounds, with the side constraint that k needs to be large enough. So typically we require k at least omega of n to the 1/3. Our approximation ratios range from 1 plus epsilon to 7 plus epsilon, depending on the size of k and the weights of g. So our best result is for k, for large k and unweighted g. This is tied up to polylog n factors, as we have seen from the previous lower bound. Our third result is that we show how to solve exact SSSP in n to the 2/5 rounds. This improves on the O of square root of d round algorithm by Augustine et al. For graphs with large diameter. Our fourth result is that we show that approximations of the diameter of the local network can be achieved in sublinear time. Specifically, we show that we can get a 1.5 plus epsilon approximation in n to the 1/3 over epsilon rounds, and a 1 plus epsilon approximation in n to the roughly 0.4 over epsilon rounds. And in the next part, I want to show how we achieve those results by talking about our techniques. Our main technical contribution is the solution of an information dissemination problem, which we call the token routing problem. Here we are given a subset of nodes, which we call the senders, and another subset, which are the receivers. And the senders have tokens, each with a recipient ID from the set of receivers. Each token has a logarithmic size. So that means that at most O tilde of 1 tokens per node and round can be sent via the global network. Then the goal of this problem is that every receiver must eventually learn all the tokens that are addressed to it. So next are some definitions. Let K sub S be the maximum number of tokens per sender, and let K sub R be the maximum number of tokens any receiver must receive. And let capital K be the total workload, namely the overall number of send and receive operations that need to take place. Then we show that we can solve this token routing problem in roughly K over N plus square root of K sub S plus square root of K sub R rounds. This comes with a restriction that S and R must be roughly well distributed in the network, and we have this with high probability if S and R are sampled uniformly at random from the set of nodes. Okay, in the next 2 slides, I want to give some intuition how we solve this token routing problem. So for simplicity, let's assume that each sender and receiver need to send and receive roughly the same number of tokens, namely K. So the idea behind this token routing protocol is that we assign each helper and receiver a subset of nodes, which we call the helper sets. And these helpers are very close by to their respective sender and receiver, and the according sender or receiver can use these nodes to increase its own bandwidth over the global network. Formally, we define helper sets as follows. A helper set is a subset of nodes for a sender or a receiver, such that such a subset has size at least square root of K. Each node must help at most polylog many senders and receivers. And each helper is within square root of K hops to its respective sender and receivers. So in our paper, we show that helper sets can be computed in roughly square root of K rounds. And for this, we can use very classic algorithms, namely algorithms for computing ruling sets. So let's go through the steps of the token routing algorithm. So in the first step, we compute the helper sets as we defined them before. And this takes roughly square root of K rounds. In the second step, all the senders distribute the tokens they have to their respective helpers via the local network. And since all the helpers of a sender are within square root of K hops, this can be done in square root of K rounds. In the third step, we send all the helpers of senders send the tokens to the respective helpers of receivers. And since each sender has square root of K helpers and each receiver as well, all the K tokens can be transmitted in square root of K rounds. And then finally, in the fourth step, all the receivers collect the respective tokens from their helpers, also via the local network, which also takes square root of K rounds. This sounds simple enough, but unfortunately, this is not so easy because helpers of senders do not know helpers of receivers, and we cannot make the sets of helpers public knowledge because this would incur way too much contention on the global network. So we use hashing to remedy this. And we match helpers of senders and receivers by choosing for each pair a pseudo-random intermediate node determined via a randomly seeded hash function from a universal family. So the overall runtime in the simplified scenario is square root of k, where we have a small overall workload. But in a general case, we have a runtime of capital K of n plus square root of k sub s plus square root of k sub r. Okay, next I want to introduce another ingredient which we will use throughout the following slides. And this concept is called skeleton graphs and was first used by Ullman and Yanakakis in the context of the PRAM model. So the idea is that if we're given a graph and we sample roughly x skeleton nodes uniformly at random, and then we consider a given UV path, the shortest UV path, then there will be a sampled node roughly every n over x hops on this shortest UV path with high probability. And if we look at a graph that we obtain when we add paths with at most n over x hops between these skeleton nodes, with the weight corresponding to the weight of the shortest path, then this resulting skeleton graph has all kinds of nice properties. So for example, the skeleton graph is connected if the original graph is connected, and the skeleton graph preserves distances of g. Another nice property is that if we're given a shortest path from u to v, which has at least roughly n over x hops, then this path must run over the skeleton graph. Okay, now we have all the tools that we need to solve the Exakt APSP problem. So the basic steps stem from the previous algorithm by Augustine et al., and we speed up a key step which constituted a bottleneck in the previous algorithm. So in the first step, we sample roughly square root of n skeleton nodes, which can be done in constant time. In the second step, we compute all roughly square root of n hop paths via the local network, which takes the same amount of rounds since we have to look that deep in the local network. And this already takes care of paths which are shorter than square root of n hops because we know their distance exactly. Then in the third step, we make the skeleton graph public knowledge. And this uses the token dissemination protocol from the paper by Augustine et al., where we can disseminate k tokens in square root of k rounds. So since the skeleton graph now has at most n edges, we can make those edges public knowledge in square root of n rounds. Since now each node has public knowledge of the complete skeleton graph, each node can compute its own distance to every skeleton node. And what we actually want is this the other way around. So we want that each skeleton node learns its distance to every other node, because we can easily enhance such a solution for the whole graph. So what we do is the following. Consider a given node, which is not a skeleton node. Then this node creates a token containing its distance to all skeleton nodes within square root of n hops. Since this node knows its distance to each skeleton node, it can decide which skeleton node needs to receive which token. So what we end up with is the following token routing problem, where the set of senders are all the nodes, the set of receivers are the skeleton nodes. Each sender has to send at most square root of n tokens, because there are only that many receivers, and each receiver needs to receive at most n tokens. And the overall workload is n to the 1.5. And plugging this into our formula for the token routing problem, we get that this whole step 4 takes square root of n rounds. And After this, every skeleton node can compute its distance with this token it received to every other node in the network, and then it can, in another square root of n rounds, send all the distance information to all other nodes to its neighbors within square root of n hops. And that solves the exact APSP problem. Another nice application of token routing is that we can simulate the CLIQUE model on a small skeleton graph. So assume that we sample roughly n to the x skeleton nodes, then we can simulate CLIQUE on this skeleton nodes, where each node needs to send a token to every other node by just running token routing with the following parameters. Plugging this into our formula for solving the token routing problem, we get that we can simulate one round of the CLIQUE model on the skeleton nodes in roughly n to the 2x minus 1 plus n to the x over 2. Let me mention at this place that the local computations on the skeleton graphs for constructing the skeleton graph, but also for extending a solution from the skeleton graph to the whole graph, both takes roughly n to the 1 minus x rounds. Being able to simulate the CLIQUE model on a small skeleton leads to a whole array of results by simulating fast shortest paths algorithms for the CLIQUE model on the hybrid model. So one of the more noteworthy results is that we get an improved algorithm for the exact SSSP problem. For this, we can use the following results that by Sensor-Hillel et al., that we can solve SSSP in n to the 1 over 6 rounds in the CLIQUE model. So the first step is to simply compute a skeleton graph as we did before, but this skeleton graph always includes the source and has roughly n to the x nodes. As we've seen before, this takes roughly n to the 1 minus x rounds. Then in the second step, we simulate the CLIQUE model on the skeleton graph and solve SSSP on the skeleton graph with the above algorithm. And this has this running time, the running time of the simulated SSSP algorithm times the runtime of a single round. And keep in mind that the number of nodes in the simulated CLIQUE model is n to the x. So we have a runtime of n to the x over 6 for the SSSP algorithm on the skeleton. And then in the third step, we extend the solution of the skeleton to all nodes in V, which takes another n to the 1 minus x rounds. And by optimizing for x, we get an overall runtime of n to the 2/5. So the final result I want to talk about is about approximating the KSSSP problem using CLIQUE simulation. For this, we can use the following result by Sensor-Hillel, which says that we can solve the APSP problem in the CLIQUE model with a multiplicative error of 2 plus epsilon and an additive error of 1 plus epsilon times the heaviest weight on the shortest path from U to V in roughly polylogarithmic rounds. So imagine the red nodes are sources. Then in the first step, we compute the skeleton with roughly n to the 2/3 nodes. In the second step, each source picks its closest skeleton node as its representative. Then in the third step, we make all the distances from sources to their representatives publicly known. And since we have k sources, this takes square root of k time. Then in the fourth step, we simulate the CLIQUE model on the skeleton to approximate the APSP problem. And then finally, in the fifth step, we extend the solution from the skeleton to the whole graph. And now every node can compute its distance to every source, leveraging the knowledge of the distance to every skeleton node and the knowledge of the distances from representatives to sources. So overall, we get that we have a 7 plus epsilon approximation. And let me just tell you that the additive error is actually not that important, since we can compute shortest paths with a certain maximum number of hops exactly. So the additive impact of this error on longer shortest paths is actually not that much. And the main contribution of this error is from the distances from representatives to sources. And then we get this overall running time, and this is O of square root of k for k bigger than n to the 1/3. So it's almost tied up to polylog factors, stemming from the fact that solving k SSSP takes at least omega of square root of k rounds. Let me conclude with a quick summary. We introduced a novel information dissemination protocol, namely the token routing protocol. And in fact, this has already led to better results by other groups down the road, which might appear in the future. In our paper, the token routing protocol leads to almost optimal algorithms for the all-pair shortest path problem and the k-source shortest path problem. And in fact, we can use a similar argument to approximate the diameter in n to the 1/3 rounds, just by observing that the diameter of the skeleton is a good approximation for the diameter of the whole graph. In our paper, we try to be a bit more efficient by providing a framework algorithm that automatically transforms a given CLIQUE algorithm into an according algorithm for the hybrid network model. So future improvements for, say, approximation parameters in the CLIQUE model have direct implications for algorithms in the hybrid model. I also want to draw some attention to our lower bound for of n to the 1/3 for the diameter problem, which uses adapted worst case graph for the congest model. And we believe that this technique might be applicable to other problems in the hybrid model. Thanks for listening to this presentation. We are open for questions in the upcoming PODC conference.